All right, guys, here is, this is a Doppler effect problem. NASA's checking in on one of its satellite probes. The probe emits a known frequency. So we have a known frequency of 5 times 10 to the ninth. Frequency's hertz. NASA detects the probe's frequency at 5.6 times 10 to the ninth hertz. Now, so why are the frequencies, if it's emitting 5 times 10 to the ninth and we're receiving 5.6, why is there a shift in frequency? That's the Doppler effect we talked about. The probe is in motion and coming toward us. So it shifted the frequency up higher. And then how fast is the probe going? We're looking for V. So we need to distinguish between these two frequencies. The 5 times 10 to the ninth is the original frequency. So we call that 5 F naught. The frequency in different books do different subscripts and stuff like that, but we're going to use F naught for the original frequency. And then the shifted frequency, or the observed frequency, is going to be what we call F prime, 5.6 times 10 to the ninth. The Doppler equation looks a little rough, but again, we don't have to memorize equations. You're going to get, so the shifted frequency is going to equal the original frequency times the square root of the speed of light plus or minus the speed of the detector over c, then you do minus plus the velocity of the source. Sorry, that's a U. And then you use the top plus or minus. Some books write this as two separate equations. I'm just trying to simplify it. Not simplify it, but give you less to write or less to look up. You just use the top ones when it's towards. So towards is top. And if it was going away from you, then you would use the bottom. You'd use the negative and the plus. So F prime is 5.6 times 10 to the ninth. I didn't leave myself enough room. Here, let's move this over. This is going to be a lot of writing. So you get 5.6. Here, you're going to get bogged down with, the math's going to look a little ugly, but it's not. I'll walk you through it. 5.6 times 10 to the ninth. This one's 5 times 10 to the ninth. Now we got square root C is 3 times 10 to the 8th. Plus, well, the detector is us. We're going to do everything relative speeds. So we can just zero out the Earth. Even though it is moving, we're going to say it's not moving, and then what that's going to give us is the probe speed compared to the Earth. So we make the detector 0, and you can always do that. It doesn't have to be the Earth. Over 3 times 10 to the 8th. Sorry, this square root side goes all the way down to here. Minus the velocity of the source, which is what we're looking for, the probe. And so I'm going to pause here and do a little math, and we'll talk. So here, what I'm doing in blue here, you don't have to write out for me. Sorry, this lighter shade of blue. You're going to take both sides and divide out. So before we do anything under this square root, because we need to get the velocity of the source by itself. Before we do anything to that, we got to get rid of this 5 times 10 to the ninth. We just divide it to the other side. So we divide both sides by 5 times 10 to the ninth, and then to get rid of the square root, we square it. So we end up with 1.25 equals 3 times 10 to the 8th over 3 times 10 to the 8th minus V, which is what we're looking for. It looks like the 3 times 10 to the 8th could cancel. They don't, because you have the minus V. So we got to do some more math. So I'm going to simplify this down a little bit. Well, not simplify. I'm going to rearrange it first, then simplify it. But how I got this 1.25 is I took 5 times 10 to the ninth and divided it to the other side. So I did 5.6 times 10 to the ninth divided by 5 times 10 to the ninth. So that got rid of that. Then I squared it to get rid of the square root. Now I'm going to rewrite this. I'm going to swap these, right? I'm going to take 3 times 10 to the 8th minus v equals, and I'm going to divide 1.25 to the other side, equals 3 times 10 to the 8th over 1.25. And then we can solve for v, right? Pause it. All right, now this equation, and then doing the math, I found a mistake. This is not right. One, it's in hertz and not meters per second. So I must have copied over from another problem and never put the proper answer in. So you take 3 times 10 to the 8th divided by 1.25, and then you subtract 3 times 10 to the 8th. So we're going to get a negative v, that v is still negative, equals a negative 6, and then 2, 4, 6, 7 times 10 to the 7th. And then the negatives go away, right? So v equals 6 times 10 to the 7th meters per second, which is ridiculously fast, which we are not there yet, just to put that out. So when we do these Doppler effect problems on situations that are more reasonable to what speeds we can achieve, the numbers are going to be crazy, have a lot of decimal places typically, because the shift in frequency is going to be super small. There is another form of this equation that handles super small frequencies, but instead of it's like it estimates them for you, or average. I don't know if average is the right word, but it gives you an estimate of it. I just avoided that by giving you numbers with very small frequency changes so that you could get a realistic number. But there is another equation that is actually used for that. But we're just going to stick to this one.